Okay, in this recording, we are going to talk a little bit about springs. What we know about springs, we can stretch them to certain amounts and then they regain back their shape. Now, as long as they regain their shape, we say that they are within their elasticity limit. You see the term here, elasticity limit. Now, when springs are within their elasticity limit, they obey what we call Hooke's law. Hooke is a contemporary of Newton. He was quite good himself, and actually he was quite a foe of Newton, and it's an interesting thing. If you are interested in stories, it would be an interesting thing to read about quarrels between Newton and Hooke. Now, according to Hooke's law, the amount by which a spring stretches is proportional to the force used to stretch the spring. Okay, when we use the word stretching, that word is applicable for compressing. The amount by which, probably the more correct term, the amount by which a spring is going to change in length is going to be proportional to the force that we apply to stretch it. Now, this is the way it is written. F is equal to K. K is a constant times X. X is by the amount by which the spring had been stretched beyond its elasticity limit. The amount by which the spring is either stretched or compressed from its equilibrium position. Now, K is what we call, actually it's supposed to be small k, is what's called the spring constant. It is a constant that's specific to the spring. Every spring is going to have its unique K. It is something that we can measure, we can figure it out, and we'll talk about it in a little bit. But the unit of K is newtons, the unit of force, divided by the unit of a displacement, which is meters, so it's newtons per meter. Now, the key thing that we need to remember, it is applicable only if we don't stretch the spring beyond the elasticity limit. Okay. Before going on to more details about that, I would like to pull up this simulation by FET. I have the URL there in the bottom. It's quite a neat simulation. What we have here, we have a bunch of springs. I already kind of suspended a mass there. So you have some known masses that you can actually put there. And the minute you put the mass and you let go of it, it's going to act like somewhat of a regular spring. And you are going to have an amount by which the spring is going to stretch. For example, here it's stretched 50 grams. We can measure how much is stretched due to 50 grams. We can measure the amount by which it's stretched. Then we can, let's say, add 100 grams. Oh, oops. I thought I remember it used to. I used to be able to put them together, but I might be wrong. I might be remembering something else. And here we go. So we have the different position for 100 grams and so on. You can keep on increasing masses and measuring the amount by which it stretches over the equilibrium position. Okay. Now, one thing interesting is the simulation is not just for use to study Hooke's law. It is actually for studying the oscillation of springs. For example, here, if I pull it beyond the new equilibrium position, the equilibrium position with the mass hanging, I can get it to oscillate. There is a stopwatch I can use to time it, and I can set the gravitational field as Jupiter, Moon, or a planet X, an unknown that I will need to find. And then I can also look at energy, various energies. I can set up an ideal spring with no friction, or I can set up the friction level of a spring. And I can change the spring constant on the third spring by acting here. Okay, let's see. See here, this is what we mean by compression. What I'm saying here, the force exerted to compress it this much is the same as the force exerted to stretch it by the same amount. And that force is given by the constant of the spring K times X, the amount by which we stretch the spring. And remember again, we measure X relative to the equilibrium position that's demarcated by the dashed line here. Okay. Now, what does the spring constant depend on? It depends on the shape of the spring, its size, what is it made up of, how is it made. All the physical characteristics of the spring are going to play a role in determining the spring constant. Usually when you buy spring, it's going to come with a value telling you how much it is, or you can actually measure it like what we are talking about here. Let's take an example here. When we suspend a mass of 2 kilograms, a spring stretches by 10 centimeters. What is the constant of the spring? Okay, so we have a vertical spring. It is sitting here at equilibrium. We hang a 2 kilogram mass. And they tell us it stretches by 10 centimeters. Now they're asking us what's the spring constant. Now the key here, the force that we have exerted to stretch it is equal to the gravitational pull of the mass. So actually on the mass we have two forces, Fg and the spring force. The spring force is given by Kx in magnitude, and the gravitational force is given by mg. Since the spring is in equilibrium here, these two forces are balanced, so I can write that Kx is equal to mg. So here, that gives us K, that's going to be mg over x, which is in this case 2.0 kilogram times 10 meters per second squared over 10 centimeters. Okay, the 10 centimeters, of course, I have to convert it to meters. That would be 0.1 meter, so that's going to be 20 newtons, that's the numerator, over 0.1 meters. So that's going to give me 200 newtons per meter. That's my spring constant. Now, how much would it stretch if we suspend a 6 kilogram mass? Now, if we suspend a 6 kilogram mass, it's going to be the same equation as we wrote here, with the K that we just found. The only difference is going to be in X and M. So we write that same equation, but in this case, we'll solve for X. So X is mg over K. In this case, M is 6 kilograms times G 10 meters per second squared, and then over K, which is 200 newtons per meter. Now this is 6 times 10, 60. 60 over 200. So that would be 0.3, I believe. Yeah, 0.3. 0.3 meters. One thing that I would like you to notice, the 0.3 meters is 3 times the 0.1 meter we had initially. And that's because we have 3 times the mass. This is the meaning of having or of saying that the amount of stretching of a spring is going to be proportional to the force. So when I triple the force by having 3 times the mass, I will get 3 times the stretching. And again, this is applicable only as long as we don't exceed the elasticity limit.